Questions 11 through 20 on the 2003 Grade 8 AMC 8. Business is a little slow at Lou's Fine Shoes, so Lou decides to have a sale. On Friday, Lou increases all of Thursday's prices by 10%. Over the weekend, Lou advertises the sale 10% off the listed price. Sale starts Monday. How much does a pair of shoes cost on Monday? That costs $40 on Thursday. So on Thursday, the shoe costs $40. And then on Friday, he increases the prices by 10%. So this shoe now would be $44. And then what he does on Monday is he has a 10% off sale. So now the price is going to go down by 10%. So you multiply by 0.9 to get the new price. And that is 39.6. All right. So 11 would be B. When a fair six-sided die is tossed on a tabletop, the bottom face cannot be seen. What is the probability that the product of the numbers on the five faces that can be seen is divisible by 6? So a die has the numbers 1, 2, 3, 4, 5, 6, correct? And the product, of course, 1 times 2 times 3 times 4 times 5 is 720. Now what I'm going to do is make a list and put the product and the bottom face. The bottom face is the face that cannot be seen. And since we can't see it, we want the product of the other five faces that can be seen. So let's say the bottom face was 1. The other five faces would be 2, 3, 4, 5, and 6. What is their product? Well, it's 720. All right? Let's say the bottom face is 2. Now we take the product of 1 times 3 times 4 times 5 times 6, and that's 360. If the bottom face is 3, the product would be 240. If the bottom face is 4, the product would be 180. If the bottom face is 5, the product would be 144. And finally, if the bottom face is 6, the product would be 120. They want you to figure out how many of these are divisible by 6. These numbers, 720, 360, 240, 180, 144, 120. Well, all of them are divisible by 6. So the probability, since all of them are divisible by 6, is 6 over 6, which is 1. So number 12, the answer is E. 14 white cubes are put together to form the figure on the right. The complete surface of the figure, including the bottom, is painted red. The figure is then separated into individual cubes. How many of these individual cubes have exactly 4 red faces? So we'll make a little table, number of cubes and number of red faces. So you have to do a little bit of visualization here. And there's 14, right, total? Yeah, 14. So this total at the bottom's got to be 14, just to keep track of things. So now let's start with 3 red faces, right? Because I think that's the minimum. 3 red faces are basically the ones that are in the corners right here. This guy right here. That's going to have 3 red faces because the other faces are basically covered. They won't be able to be painted red. So how many of those corners do we have? We've got 1, 2, 3 over there, and 4 corners. So there's 4 cubes that have 3 red faces. How about 4 red faces? Those are going to be these guys in the middle, like that. You can see that one there. So we got 1, 2, 3, 4, 5, 6. 6 of those. And then 5 red faces. If you look at this diagram more carefully, you will see that there's 4 of those guys. It's basically these ones up top. 1, 2, 3, 4. Those will have 5 red faces when everything gets colored that is visible. So does this total add up to 14? 4 plus 10 plus 4 is indeed 14. And how many of the individual cubes have 4 red faces? And the answer is 6. So number 13, the answer is B. In this addition problem, each letter stands for a different digit. If t is equal to 7 and the letter O represents an even number, what is the only possible value for W? So we have T, W, O, T, W, O, F, O, U, R, like that. All right, T is equal to 7. So instead of T, I can put 7 in here. So I'll do that. And let's see what we get if we do that. 7 plus 7 is 14. So that basically means that these two are 1 and 4, like this. And we now have to figure out what is W. Well, O represents an even number. So let's see, what can it possibly be? Well, let's try the smallest even number, which is 2. If O is 2, then we'll have 2 and 2, and we'll have 4. But this is not allowed because each letter stands for a different digit. O cannot be the same as R, which is essentially what happened when we made O equal 2. That's not going to work. All right, fine, no problem. Let's make O equal to 4. And it is 4, right? We already made it 4, so there was no reason to even choose anything else. So we just go with that. If you have 4 for O and O, just like I have up here, R will become 8. Okay, so far everything's fine, right? We have different digits for everything. Now we have to turn our attention to W. Well, what can W be? Let's start off with 0. If W is 0, then this becomes 0, this becomes 0, and that will be 0. Like this, 0 plus 0 and 0. But W and U cannot be the same. That's essentially what happened in that scenario. So that's no good. How about, can W be 1? No, because 1 is already taken. That's the value for F. Can W be 2? Well, we can try that, but if you do that, you'll get 4 for U, and 4 is already the value for O. So it can't be 2. How about 3 for W? 3, 3, and 6. Is there any conflicts here? And the answer is no. No conflicts. So W equal to 3 works and fits all the criteria. So number 14, the answer is D. A figure is constructed from unit cubes. Each cube shares at least one face with another cube. What is the minimum number of cubes needed to build a figure with the front and side views shown? So you got to do a little bit of visualization here. So they've given you the front like that. They've told you that's what it looks like. And we have to sort of figure out the side. The side is going to look something like this, basically. And they've told you that. And now we kind of have to make it look like a shape. Something like that, right? In a very, very basic way of combined the front and the side. And then now they're asking, what is the minimum number of cubes needed to build a figure like this? Well, just count them. You got 1 here, 2, 3, and 4. Right? That's the minimum number. So 15, the answer is B. Annie, Bonnie, Carlo, and Diana are going to drive together to a nearby theme park. The car they are using has 4 seats, a driver's seat, a passenger seat, and 2 back seats. Bonnie and Carlo are the only 2 who can drive the car. How many possible seating arrangements are there? So you got driver, passenger, back 1, and back 2. Now, if I were to put them in sort of a row like this, I can get the number of possibilities for each of these. Now the good news is that they tell you a very important clue that Bonnie and Carlo are the only 2 that can drive. So we only have 2 scenarios. The first scenario is that when Bonnie is the driver, and the second scenario is when Carlo is the driver. If Bonnie is the driver, for the passenger seat, who can sit there? Well, there's 3 other friends, so any of those 3. How about the first back seat? Well, there's 2 remaining friends, and the very last remaining friend. So if Bonnie is the driver, there's 3 times 2 times 1, which is 6 possible seating arrangements. If Carlo is the driver, in the exact same way, it's 3 times 2 times 1, which is 6 possible seating arrangements. And to get the total, you add them. And if you add them, you get 12. So number 16, the answer is D. The 6 children listed below are from 2 families of 3 siblings each. Each child has blue or brown eyes and black or blonde hair. Children from the same family have at least one of the characteristics in common. Which 2 children are Jim's siblings? So here's Jim. So we're going to concentrate on him. His siblings have to have eye color that's brown, or they have to have hair color that's blonde, because children from the same family have at least one of these characteristics in common. So the first thing we can do is eliminate people who do not have brown eye color and also do not have blonde hair. They cannot be Jim's siblings under the criteria. So who does not have brown hair? Or eye color, I mean. We've got Benjamin and Austin and Tevin and Sue. A lot of people. And then who does not have blonde hair? Benjamin and Tevin. Benjamin and Tevin are basically not possible to be Jim's siblings because they don't have brown eye color and they don't have blonde hair. So Benjamin and Tevin are gone. Now they want you to figure out 2. Only 2 are Jim's siblings, but we've left with Nadine, Austin, and Sue. Right? We're left with 3 people. All right, we got to figure out which one of those is not. So what we need to do is compare Nadine and Austin and Sue to each other. Let's look at Nadine. She has brown eye color, right? Austin has blue, and Sue has blue. So it looks like Nadine is probably the odd one out. But let's keep going. Her hair color. Her hair color is black. Austin is blonde. Sue is blonde. Nadine does not have the same eye color or hair color as Austin or Sue. So she cannot be part of that family based on the criteria. So the only 2 that are left are Austin and Sue. And those are the siblings of Jim. So number 17 is E. Each of the 20 dots on the graph below represents one of Sarah's classmates. Classmates who are friends are connected with a line segment. For her birthday, Sarah is inviting only the following: all of her friends and all of those classmates who are friends with at least one of her friends. How many classmates will not be invited to Sarah's party? First, let's count Sarah's friends. Those are the ones that directly connected to Sarah. Here's 1, 2, here's 3, 4, 5, 6, 7, 8, and 9. So her friends has 9 friends. And in addition to all of her friends, she's also inviting classmates who are friends with at least one of her friends. So I guess the ones that are joined to her friends. So I'll color those in green. This is connected to a red. This is connected to a red. This is, and I think that is it. Let me double check here. Yes, indeed. So friends of friends are 5. And these are the people that she's inviting. So 9 plus 5 is 14. So there's 20 classmates in total, and she's inviting 14. So how many is she not inviting? Well, 20 minus 14, which is 6. So number 18, the answer is D. How many integers between 1,000 and 2,000 have all three numbers 15, 20, and 25 as factors? So this is one of those questions where we have to find the LCM, least common multiple. And the best way to do that is to break up the numbers into their prime factors. So 15, 20, and 25. 15 is 3 times 5. 20 is 4 times 5. And 25 is 5 times 5. Like that. I can further break down 4 times 5 into 2 times 2 times 5. This is basically making it into prime numbers. Now, which is the least common multiple? Least common multiple in 15, 20, and 5. Look at the prime factors and what's common to all three. 15 is 3 times 5, 20 is 2 times 2 times 5, and 25 is 5 times 5. What's common? Is 3 common? No, 3 doesn't appear here or here. How about 5? 5 is common. It's part of the factors of 15. It's part of the factors of 20, and it's part of the factors of 25. All right? So that's the least common multiple. But not quite, because we have to actually figure out that as a combination of all three. All right? So how do we do that? What we do is we just take the other prime factors. So we take 3, 2, and 2, and 5, multiply them. So we have 3 times 2 times 2 times 5. And then the one that's common to all three, you only use once, because it only needs to be used once. All right? So this is your least common multiple. You see how it had to be combined? And this is obviously a number, so 3 times 4 times 25 is 12 times 25, which is 300. So 300 is basically a number that has all three of these numbers as factors. And we have to figure out how many of these are between 1,000 and 2,000. Well, 300 obviously is not in between 1,000 and 2,000, but a multiple of 300 would be. So how about 1,200, 1,500, and 1,800? These are multiples of the least common multiple, and therefore these will be divisible by 15, 20, and 25. So I hope that made sense. And number 19 is therefore, how many do we have? We've got 3 of them, so it's C. What is the measure of an acute angle formed by the hands of a clock at 4:20 a.m.? So let's draw our little clock here. And as we all know, in the 4 o'clock position, we're going to basically have the minute hand pointing directly at the top. So like that. And the hour hand will point basically to the 4. So like this. All right. So this is 12. This is the big hand. This is the small hand, like that. And then at 4:20, the small hand, which I'll draw in a different color, will move a little bit like this, a little bit like that. But the big hand will come all the way down to, interestingly, to 4. That's how you get 4:20. And we want to know, what is this tiny little angle in between there? Right in there. All right, no problem. When the hour hand, this tiny guy, moves between one number to the next, so I'll draw the 6 here and then the 5 here. When it's going from one to another, we've got to look at the angles. So for example, when you're going from, say, 4 to 5, like that, it's going to move how many degrees? If the small hand was going to go from 4 to 5, it's basically going to go 1 over 12. 1/12 of the full rotation around. And one rotation around is 360 degrees. So you're going 1/12 of that, right? Because you're just going over one number of the 12. So 360 divided by 12 is 30 degrees. All right. So if we were to go from 4 to 5, from here to here, that would mean it would be 30 degrees. 30 degrees. Okay. But we're not going from 4 to 5. We're going from 4 to this position right there. That little guy there. Well, how do you figure that out? Well, how many minutes did we go? We went 20 minutes, right? Because it's 4:20. 20 minutes over an hour. And you multiply that by how much you would go in an hour, which is 30 degrees. And then you do the math, you get 600 over 60, which is 10 degrees. All right. So number 20, the answer is D.